Alright, so we talked last time about the LaPlace transformation and some properties of that, and hopefully that homework was okay using those ideas. Today we want to think about the idea of an inverse transformation, and I told you that's where we were headed with all of that, is we want to transform something, work with it, transform it back, and that'll provide for us a solution. So I won't have to do a whole bunch of different techniques, at least not for these kind of problems. It actually works out pretty nice. And I told you on the first day that it was a algebraic approach rather than a calculus approach, so that's nice as well. So just a couple of things about notation. Given a function of t, that's what we've had, given a function of t, then that provided for us a function of s, right, when I applied the LaPlace transformation. So little f of t, big F of s. And so with an inverse, and I'll use the inverse notation, well, I really should have braces there, but at any rate, then I end up back where I started. That's the goal. So today we want to take something that's already been transformed theoretically and then turn it back into a function of t. The only thing that's going to happen today is, and it happens, you've done it so many times you don't even think about it anymore. When I say fix the u and the du, you know exactly what that means. If I need a number in the du in integration, we put that in and take it back out. So we pull all of those tricks are still fair tricks to use on these problems. So let's look at some problems on page 374, beginning with problem number 2. Number 2, I want to transform back, I want to take the inverse transformation of 2 over s squared plus 4. And so your second page that I gave you on Canvas that has the inverse transformations on it. Again, y'all, I have a finite number of these, so I've got to find one that fits the form. So in particular, I needed, for this problem anyway, an s squared and something else squared. So it sort of kind of looks like this one. I'm tempted to use the cosine, but it has an s, and that s is the variable, right? So it would have to already be there. B is a constant, so I can deal with the constants without any issue. So this problem, I think, is going to exactly fit this form, right? I can rewrite 4 as 2 squared, and then there's already a 2 in the top. That fits the form exactly. And so this is equal to the sine of bt, in this case, the sine of 2t. So everything was there. Again, I just had to recognize what form it would look like. Okay, I want to work one that I didn't choose out of the book, just so you'll see it. If I do the inverse transformation of, say, 5 over just s minus 3. 5 over s minus 3. So again, I need just an s to the first power, so that limits my choices. So an s to the first power, maybe could use this, but I think it looks most like this second function. It certainly looks like the first, doesn't it? But I've got that extra number down in the bottom. What I don't need is the 5. So I can factor the 5 out. So I have the inverse transformation of 1 over s minus 3, which looks exactly like the second option there. And that option says e to the 3t power. And of course, in this problem, times 5 times that 5 that I factored out. Okay, so any of those options are fair game. Look at number 4, kind of with that idea of a constant in mind. I want to take the inverse transformation of 4 over s squared plus 9. Alright, so that looks almost exactly like number 2, but I need this to be something squared. Well, we can do that, but I need this to be the something in the numerator, right? So let me just start with that denominator. I think I can rewrite it as s squared plus 3 squared, and then it's beginning to fit that form. What I don't need, though, is the 4, so I'm going to factor the 4 out. But what I do need is, if I have a b squared on the bottom, I have to have a b in the numerator. But you already know where this is going. I can't just go around putting new numbers in without also taking them back out. If I multiply 4/3 times this fraction, I'll get this original problem back. But this now fits the form. So I have 4/3, and it looks like that's going to be the sine of 3t. Just like number 2, but with that extra 3t in there. Look at number 8. Number 8 says 1 over s to the 5th. And the inverse transformation of that. So the closest thing that I can find to that, I need just an s on the bottom and s to a power. I think it's going to be this third option. So my problem says s to the, the 5th. So I need to rewrite that as, instead of 5, as something plus 1. And then I need the something factorial in the numerator. So I can rewrite this as s to the 4 plus 1 power. Right, that's the original problem. 4 plus 1 is 5. But if I'm letting n be 4, then I need a 4 factorial. And I need to take it back out. Just like in calculus when we do the du portion. Okay, so what's in braces now, I can transform, and it is exactly t to the 4th. And then I need to worry about this 1 over 4 factorial. 4 factorial is what, 24? 4 times 3 times 2 times 1. Okay, so far transformations aren't bad, and they're really not. It's making it fit the form always. So I want to show you just a couple of other ones that get a little bit more interesting. Look at number 6. I want to do the inverse transformation of 3 over 2s plus 5. Alright, so the first thing I notice is that it's 2s plus 5, and all of my inverse transformations are just an s. So I'm going to need to deal with that. I need to get that to be an s and not a 2s. I need to think about a little bit of algebra here, so let's just think about that. Let me write in another color. Maybe you can see these other colors. If I just think about that as being 2s plus 5 to the 3rd power, alright, if it was just one of those, it would be real easy to multiply through by, say, a half. A half times 2s, that would give me just an s, and it would also give me a 5 halves. But that 1 half, I can only multiply it one time. So I have a half there, I have a half I need here, and I have a half here. So really, what I'm needing to multiply by to fix that is a half times a half times a half, or a 1/8. A 1/8 will kind of reorganize that for me. So think about what that's going to do. It's going to get rid of this, and it's going to put a 2 back in this piece. Okay? Now, I've multiplied through by the 1/8. Well, that changes the value, doesn't it? So let's think about that fraction now. Sorry, I want that to be just an s times a half. That's going to go away, and times 5 is 5 halves. Right, but I need to do that 3 times to make it be something cubed. Alright, so if I multiplied a half down here, I can't just go around multiplying halves, or really 1/8 to the denominator, without also multiplying 1/8 to the numerator. Think about why. What's the value of this fraction? This value is 1. I've used this in the bottom and changed it into this. but I still have a 1/8 in the numerator that I don't want, right? I need a 1 sitting there. Isn't that the transformation? Where did I do my list of transformations? Let me just write a little bit maybe. So we've got a 3/8 in there right now, right? That 3 is this 3. The 1/8 came from multiplying, and then I literally did the multiplication to get it cleaned up in the denominator. All right, I don't think I need a 3/8 in there, so let me now take the inverse transformation of s minus 5/2. I need it to fit a form though, right? S minus 5/2, it looks like, do I have a s minus or plus anything to a power? I think the only one that I have is down here. So instead of the third power, let me make that be the 2 plus 1 power, where n is 2. So if n is 2, I need a 2 factorial in the top, and I need to take it back out. Right? I can't just go around putting new things in without taking them back out. So this 3/8 came from reorganizing the denominator, and that extra 1/8 in the top. The 1/2 came from taking out this 2 factorial. So finally, what's in braces fits the form, and so that transformation looks like t to the n power times e to the at power. And let's see, it's actually plus, but my form is, it needs to be a s minus, so the negative 5/2 t power. So the issue here, of course, is the algebra that's going on, and that's the piece that can really bother you. The transformations up till number 6 have been nothing. Look at number 12. Number 12 says a negative s minus 7 over s plus 1 s minus 2. So again, I need to make this be in the form to be able to do a transformation. So to do that, I'm going to go back to our old friends, the partial fractions. And all the rules for partial fractions occur. I feel sure I'm not going to test you on like a non-factorable quadratic factor. But if we have repeaters, we have talked about in the past in other classes how to handle those repeaters. So at any rate, I have this, and I want to solve for a and b. Alright, I can do that by, and I'm not going to do all that arithmetic, I can multiply this entire equation by an s plus 1 and an s minus 2. And so I'm left with a negative s minus 7 equal to a times s minus 2 and b times s plus 1. Alright, remember how this works. S can be any value. A and b are fixed. So I can choose any value of s I want that solves this equation. Sometimes we have to solve maybe a couple of equations, a system of equations. But I think for this problem, if I let s be 2, then that's going to wipe out this altogether. So if s is 2, I'm left with a negative 2 minus 7, or negative 9, is equal to 0a plus 3b. So that tells me that b is a negative 3. And I'm just circling it so I can go back and find it in a moment. And then if I let s be negative 1, it's the same sort of idea. This factor will disappear. So I have a negative 1 equal to a times negative 1 minus 2 and b times 0. Looks like a is positive 2. So what I now have is the inverse transformation of the original is equal to a over this fraction plus b over this denominator. And by my properties of Laplace transformations, I can take the Laplace inverse transformations individually, just like with derivatives. We differentiate over addition and subtraction. So I'm going to take the inverse of 2 over s plus 1 and negative 3 over s minus 2. And y'all know I hate to put in all these steps, but since we're working virtual, I'm going to. I don't need that 2 at all, so I'm going to factor it out. Nor do I need that 3. And so both of those things in brackets, I think, exactly fit a form. That's a really easy case, and s minus a ends up being e to the at power. So this is 2e to the negative 1t power. Right, the negative came from s minus a minus plus, so we've done that enough. And e to the 2t power. So just a comment about that. That looks a lot like if I didn't have the 2 and the 3. You know, you can think about where we're going with this stuff. So I got this from the characteristic equation before. So this is sort of kind of like I have a function out there, or rather a differential equation that I'm trying to solve, and I can apply some initial conditions and actually find C1 and C2 are eventually what we will do next week. Okay. All right. Partial fractions comes up all the time in these. I honestly don't remember which ones I've assigned. But we'll work any that we need to. You may have some repeating roots with partial fractions. Let me just quickly talk about that. If I had something of this nature, and I'm not going to solve it, I'm just making it up. So if I was rewriting that as partial fractions, then I have an a over x plus 2 that I have to account for. It may not be there, but maybe. And then I might have 2 of those. So I need to deal with that a second time. And then the x minus 7 piece. All right, the ones that really get us is if I have something like this. And again, I'm just making up something. So we're good with the a minus 7 piece. It works like it always does. And that's the best case to be in, is linear factors. But for this kind of piece, we have to allow for the possibility of something of that form. And again, that's not a guarantee that any of it's there. I just have to account for it. So you've done partial fractions. It may have just been a while since you've done it, but we did it. Where did we do it in classes that I've taught you? Maybe Cal 3. I don't remember now. But at any rate, try that homework, and then next week we're going to do the whole process where we transform it, use our properties, do the inverse transformation, and that'll be our solution.